What if the mathematics we claim to have discovered was actually rediscovered? The chisel marks were still sharp, too sharp for something carved 3,000 years ago. I knelt in the red dust, tracing my fingers along grooves that formed spirals within spirals, each one nested with geometric precision that shouldn't exist in the ancient world. The sun was setting, casting shadows that revealed hidden angles in the stone. My guide stood silent behind me. When I asked what his ancestors used to create such perfection, he simply said, "Some knowledge was given, not discovered." That moment changed everything. It sent me on a path through canyons and deserts, across continents and oceans, searching for petroglyphs that defied explanation. Carvings that contained mathematical constants before those constants were supposedly known. Astronomical alignments calculated with impossible accuracy. Patterns that repeated across cultures separated by vast oceans and thousands of years. Binary code in Irish tombs. The golden ratio in Scottish highlands. Fractal geometry in Utah canyons. Pythagorean triangles carved a millennium before Pythagoras was born. Each discovery raised the same haunting question. Were they astronomers and mathematicians far more advanced than we've credited? Or did they inherit wisdom from an even older source? This is the chronicle of 15 discoveries, 15 sites where ancient hands left marks in stone that challenge everything we think we know about the development of human knowledge. Welcome to the expedition. The tunnel was barely wide enough for my shoulders. I crawled through darkness, my headlamp catching glimpses of carved stone that hadn't seen daylight in 5,000 years. The air was cool and still, thick with the weight of millennia. Then the passage opened into a chamber, and I understood why they built it. On the winter solstice, sunlight penetrates this tomb in Ireland for exactly 17 minutes, but it's the triple spiral carved at the entrance that stopped me cold. 3 interlocking spirals, each one flowing into the next with mathematical symmetry. No preliminary sketches, no mistakes. Just pure geometric precision cut into stone before the pyramids existed. The archaeologists call it art. But when I measured the ratios between the curves, I found something that made my hands shake. The golden ratio, appearing again and again in proportions that shouldn't be accidental. I spent 3 days documenting that spiral, photographing it at different angles, measuring the distances between each groove, running my fingers along curves so smooth they seemed polished by something other than stone tools. The groove depths were consistent to within millimeters. The curves maintained their proportions as they expanded outward. Whoever carved this understood that certain ratios create visual harmony, that mathematics and beauty are inseparable. Dr. Murphy from Trinity College joined me on the second day. She brought calipers and ratio calculators, tools that would reveal what my eyes suspected. We measured the distance from the center of each spiral to successive turns. The ratio kept appearing, 1.618, phi, the golden ratio, the same proportion that governs seashell growth, flower petal arrangements, and the dimensions of the Parthenon. But this was carved around 3,200 BCE, over 2,000 years before Greek mathematicians gave it a name. The implications were staggering. Either this was coincidence, which seemed mathematically impossible given how consistently the ratio appeared, or the Neolithic builders of Newgrange possessed sophisticated geometric knowledge. They understood proportion. They understood how to translate abstract mathematical relationships into physical form, and they chose to encode that knowledge at the entrance to a structure aligned with celestial precision. But here's what haunted me as I sat in that chamber. waiting for the setting sun to angle through the passage. The spiral wasn't just decorative. It was positioned exactly where anyone entering would see it first. It was a statement, a declaration carved in stone. We know, we understand, we've seen the patterns that govern growth and form, and we've built this place to prove it. The curbstones outside showed more patterns, spirals and lozenges, circles and wavy lines, all carved with the same inexplicable precision. I documented over 40 different geometric designs, each one executed with a level of skill that suggested these weren't primitive scratchings. These were the works of specialists, people whose sole purpose was creating mathematical art in stone. As darkness fell and I prepared to leave, my light caught something I'd missed. Faint marks on the chamber ceiling, barely visible after 5 millennia of darkness. More spirals, smaller, more densely packed. Someone had carved them where almost no one would ever see them. That's when I knew I wasn't just looking at decoration or religious symbols. I was looking at knowledge being preserved, mathematical principles being encoded for future generations. But what other principles had they hidden in plain sight? And would I find similar precision in the desert where ancient hands had scraped away stone to reveal impossible geometric truths? The desert stretched endlessly in every direction and I was lost. Not geographically, I had GPS, but mentally. I stood before a massive geoglyph etched into the Chilean hillside, a perfect square containing a circle, containing another square, containing another circle. 4 iterations deep. My mathematician colleague Maria was running calculations on her tablet and her face had gone pale. The ratios between each shape were approaching pi with an accuracy of 99.8%. These weren't made with laser levels or computer software. They were made by people scraping away dark surface stones to reveal lighter rock beneath, sometime around 1000 CE. The scale was overwhelming. The outermost square measured nearly 80 meters on each side. To create something this large with mathematical precision required planning beyond anything I'd encountered. How did they maintain straight lines across such distances? How did they ensure the circles were truly circular, not oval or irregular? I walked the perimeter of the outer square, counting my steps. 760 paces to complete the circuit. The corners met at perfect 90-degree angles, verified by the compass on my phone. No deviation, no approximation. Whoever designed this understood that squares have equal sides, and right angles aren't suggestions, they're requirements. But maintaining that precision while removing thousands of stones by hand, that required a system I couldn't fathom. Maria called me over to the southern edge. She'd been measuring the nested circles, calculating their diameters and circumferences. The numbers told an impossible story. Each circle's diameter related to the next by a consistent ratio, and when she divided any circle's circumference by its diameter, she got pi, not close to pi, not approximately pi. 3.14, accurate to 2 decimal places, carved into a hillside by people who supposedly had no formal mathematical training. But here's what haunted me. As the sun climbed higher, turning the desert air into shimmering waves, pi is an irrational number. It goes on forever, never repeating. You can't derive it by simple measurement. You need geometry, theory, abstract thinking. The ancient Greeks struggled with it. Medieval mathematicians obsessed over it. Yet someone in the Atacama Desert, working with string and stakes and human labor, had encoded it into the landscape with stunning accuracy. We spent 5 days at that site, documenting every measurement we could take. The angles, the distances, the proportions. Each calculation confirmed what seemed impossible. This wasn't accidental. This wasn't close enough. This was intentional mathematical precision on a monumental scale. And it was just one of dozens of geometric geoglyphs scattered across the Atacama. On our last evening, I climbed a nearby hill to photograph the site from above. The setting sun created shadows that revealed details invisible from ground level. Small markers, piles of 3 stones, positioned at specific points around the geometry. I counted them, 12 markers, evenly spaced around the outer circle, like hours on a clock face, or months in a solar year, or perhaps reference points for creating the perfect circle in the first place. The question burned in my mind as we packed to leave. If they could encode pi into landscape geometry, what other mathematical constants had they mastered? And why did similar precision appear 5,000 years earlier, carved into stone slabs on a Scottish hillside where Victorian scholars refused to believe what they were seeing? Rain hammered the Scottish hillside as I crouched over what might be Britain's greatest unsolved puzzle, the Cochno stone. A massive rock face covered in cup and ring marks forming patterns so precise, Victorian scholars declared it must be a hoax, but radiocarbon dating confirmed its age at over 5,000 years. I traced my fingers along the concentric circles, 90 of them spread across the stone's surface, each ring spaced with millimeter accuracy. The stone had been buried for decades, covered with soil to protect it from vandalism. When archaeologists re-exposed it in 2016, I was among the first researchers allowed to study it properly. What struck me immediately wasn't just the quantity of carvings, but their mathematical consistency. Cup marks, small circular depressions, served as centers for ring systems. Some had 3 rings, some had 7, but the spacing between rings within each system followed identical proportions. I measured obsessively, working through the rain with calipers and laser distance finders. In one cluster of 7 ring systems, the ratio between the first and second ring was 1 to 1.5. Between the second and third, 1.5 again. The pattern held across all 7 systems. Whoever carved these wasn't eyeballing it. They had a measuring system, a standard unit, and the discipline to apply it consistently across the entire stone face. Dr. Morrison from Glasgow brought ground-penetrating radar on the 3rd day. We needed to know if the carvings extended beyond what was visible. What the radar revealed made us question everything. More patterns, buried under centuries of soil accumulation. Patterns that continued the mathematical sequence started above. The visible carvings weren't the complete work, they were the top layer of something larger, something planned across vertical space and potentially across generations. Some form spirals. Others create maze-like pathways that lead nowhere and everywhere simultaneously. I followed one spiral with my finger, counting the turns. 13 complete rotations before it terminated in a cup mark at the center. Another spiral nearby also made 13 turns. Coincidence? I found 4 more spirals. All 13 turns, all ending in cup marks of nearly identical diameter. The archaeological establishment called these cup and ring marks throughout Britain and Ireland. Thousands of examples exist, but the Cochno stone stands apart because of its scale and complexity. It's not a single panel, it's an entire surface covered in interconnected geometric systems that reference each other, overlap, and maintain mathematical relationships across the entire composition. But here's what kept me awake in my Edinburgh hotel room, staring at photographs spread across the bed. The cup and ring marks aren't unique to Britain. Similar patterns appear in Galicia, in Northumberland, in parts of Scandinavia. Different cultures, separated by water and distance, all creating the same geometric vocabulary in stone. Were they connected? Did the knowledge spread? Or did multiple cultures independently discover the same mathematical principles and choose the same way to express them? The rain finally stopped on our last day at the site. As evening light raked across the stone at a low angle, shadows revealed details invisible at midday. Faint connecting lines between some cup marks, barely visible grooves forming triangular relationships between circles. The Cochno stone wasn't just a collection of individual carvings. It was a unified composition, a mathematical statement carved into living rock. But the real mystery wasn't the precision, it was the purpose. And perhaps another passage tomb in Ireland, one overshadowed by more famous neighbors, held part of the answer. I'd been studying the stones of Knowth for 3 days when the pattern finally revealed itself. The Irish passage tomb sits near Newgrange, overshadowed by its more famous neighbor. But what I found here was perhaps more significant. The curbstones surrounding the mound are covered in carvings, and at first they seemed random, crescents, circles, wavy lines. But on the third night, unable to sleep, I began counting the crescents on curbstone 15, 29, the length of a lunar month. My heart was racing as I returned at dawn with my camera and notebook. I started systematically documenting every curbstone, photographing each symbol, sketching the patterns, counting the recurring motifs. Curbstone 52 had 12 full circles arranged in a deliberate row. 12, the months in a solar year. This couldn't be coincidence. I was looking at a calendar system carved in stone 5,000 years ago. But it was more sophisticated than simple counting. The builders of Knowth understood the fundamental problem that has plagued every calendar system in human history. Solar years and lunar months don't align. A solar year is roughly 365 days. 12 lunar months total only 354 days. There's an 11-day gap that accumulates over time, throwing seasons out of sync with months unless you make corrections. I found those corrections carved into the stone. Curbstone 13 showed a pattern I initially dismissed as decorative, a series of small crescents arranged in groups. But when I counted them carefully, I found clusters of 30 crescents appearing at regular intervals among the groups of 29. Someone had understood that lunar months alternate between 29 and 30 days. They'd tracked it, they'd recorded it, and they'd literally set that knowledge in stone. Dr. O'Sullivan from University College Dublin joined me on day 5. She specialized in archaeoastronomy, and when I showed her my documentation, she went silent for a long moment. Then she pointed to curbstone 67. The wavy lines I'd been puzzling over, trying to decode their meaning. She saw them immediately. Sine waves, the graphical representation of cyclical phenomena. The moon waxes and wanes in a cycle, tides rise and fall in a cycle. These wavy lines weren't abstract art. They were depicting periodicity, the concept that certain patterns repeat over time. We spent 2 more days testing the hypothesis, measuring, counting, correlating symbols across the entire curb. The evidence mounted. Some stones showed crescents in specific orientations matching the moon's appearance at different phases. Others displayed circles with radiating lines, possibly representing full moons or significant lunar events. The entire structure was surrounded by a stone-carved almanac. But here's what made this discovery profound. Creating an accurate lunar calendar requires continuous observation across years. You can't just watch the moon for a month and understand its patterns. You need to track it through seasons, through years, noting how it shifts position against the background stars, how its phases align and misalign with solar seasons. This represented institutional knowledge, information passed between generations of observers who maintained their understanding over decades. As I packed my equipment preparing to leave Knowth, one question consumed me. If they understood lunar cycles with this precision, what did they know about the sun's movements? And could ancient people half a world away, working in the deserts of South America, have achieved similar astronomical sophistication? The helicopter banked sharply, and I pressed against the window, camera ready. Below us, etched into the Peruvian desert, a spiral unwound across half a kilometer of sand and stone. But this wasn't like the famous animal figures of Nazca. This was pure geometry. A logarithmic spiral, the kind that appears in nautilus shells and galaxy arms and hurricane formations, the kind that requires understanding exponential growth. I'd spent weeks studying these lesser-known Nazca lines, the ones tourists rarely see, spirals upon spirals, some clockwise, some counterclockwise, many incorporating the golden ratio in their expanding curves. From the ground, they're incomprehensible. From the air, they're mathematical proofs. The pilot circled lower, and I could see the technique clearly. Dark surface stones had been removed to reveal lighter-colored soil beneath. Simple in concept, impossible in execution at this scale. We landed near the largest spiral, and I walked its path on foot. The line was perfectly consistent in width, about 30 centimeters, maintained across hundreds of meters. No wobbling, no corrections. Just a smooth curve that grew wider with each rotation according to a precise mathematical relationship. I measured the distance from the center to the first complete turn, then to the second turn, then the third. Each distance was roughly 1.6 times the previous one, phi again. The golden ratio appearing in the Peruvian desert, created by the Nazca people around 500 CE. But here's what kept me awake in my tent that night, listening to the desert wind. How did they check their work? How did the Nazca people, working with string and stakes around 500 CE, verify the mathematical accuracy of something they could never see in its entirety? They had no helicopters, no aerial perspective, no way to step back and view the complete composition, yet the spirals are perfect. Dr. Reich, a German mathematician who spent decades studying the Nazca lines, proposed they used scaled models and proportional enlargement. Create the design small, then multiply all measurements by a constant factor. Mathematically sound, but practically maintaining accuracy while scaling up a spiral from a 1-meter model to a 500-meter ground figure using only rope and wooden stakes requires almost superhuman precision. I found something else that week. Groups of small stones placed at specific points along some spirals, markers perhaps, reference points. I documented their positions, measuring distances between them. The spacing wasn't random. These markers appeared at points where the spiral completed quarter turns, 90-degree intervals. Someone had divided the circle into quadrants and marked those divisions on the ground, perhaps to help maintain the curve's accuracy during construction. the implications were staggering. This wasn't art for art's sake. This was applied mathematics on a monumental scale. The Nazca people were using the desert as a canvas to demonstrate geometric principles. But why? Who was the audience? The gods looking down from above? Future generations with flying machines? Or was the act of creation itself the purpose, the process of manifesting abstract mathematical beauty in physical form? As I prepared to leave the Nazca Desert, another question pulled at me. Had ancient peoples elsewhere in the world also encoded mathematical knowledge into their sacred sites? And could the oldest rock art on Earth, carved into stone tens of thousands of years ago, reveal similar geometric sophistication? The elder's hand swept across the rock face, tracing lines between carved circles and dots. We were in the Flinders Ranges of South Australia, and what I'd initially thought were random engravings suddenly snapped into focus. This was Orion's Belt. Those 3 circles, perfectly aligned, matched the stars exactly. And the wavy line connecting them to another cluster? That was the path the constellation took across the night sky through the seasons. Aboriginal Australians had been creating astronomical maps for at least 15,000 years, possibly much longer, but the precision stunned me. Using only stone tools, they'd carved star positions with accuracy that matched modern star charts. The angles between constellations were correct to within degrees. Uncle Rodney, the Adnyamathanna elder guiding me, explained that these weren't just maps, they were also navigation guides, calendars, and storytelling devices, all encoded in geometric relationships. I spent a week documenting the site, measuring angles with a theodolite, photographing each carved element, cross-referencing with astronomical software on my laptop. The 3 stars of Orion's belt were spaced proportionally correct. The angle from those stars to the Pleiades cluster matched the actual celestial geometry. Someone had transferred the 3-dimensional positions of stars onto a 2-dimensional rock face with mathematical accuracy that shouldn't be possible without instruments. But it went deeper. Uncle Rodney showed me how the carvings aligned with the horizon line visible from that specific location. Certain star clusters were depicted at the exact height above the horizon where they'd appear at specific times of year. This wasn't just mapping stars. This was mapping stars as they appeared from this precise geographical position at specific seasons. The level of observational astronomy required was extraordinary. Dr. Fuller from the Australian National University joined me on day 4. She specialized in archaeoastronomy and brought star charts dating back thousands of years, accounting for precession and stellar motion. We compared the rock carvings to where those stars would have appeared in the sky 10,000 years ago, 15,000 years ago. The match was remarkable. Whoever created these carvings had accurately recorded the night sky as it appeared in deep antiquity. 3 functions in one elegant system. Navigation, because the star paths showed directions for long-distance travel across the continent. Calendar, because certain stars appeared at certain times of year, marking seasons for ceremony and resource gathering. And story, because each constellation held cultural narratives passed down through countless generations. The geometric precision wasn't separate from the cultural meaning, it was integral to it. I found smaller carvings near the main panel, dots arranged in specific counts. 7 dots in one cluster, 5 in another, 12 in a third. Uncle Rodney explained these represented the number of days or nights certain stars would be visible before setting or rising. They were counting time using stellar events, creating a calendar not based on the sun or moon, but on the slower, more reliable movements of distant stars. As I prepared to leave the Flinders Ranges, one thought dominated my mind. If Aboriginal Australians had achieved this level of astronomical sophistication 15,000 years ago, what had other ancient cultures discovered? And could a small carved stone in Ireland, hidden in shadow for millennia, reveal mathematical concepts that wouldn't be formally recognized for another 5,000 years? I almost missed it. The carving was small, tucked into a corner of the chamber at Knowth, another passage tomb in Ireland's Bóinne Valley. But when I angled my light just right, the grooves revealed something impossible. A single continuous line carved into the stone, twisting back on itself, joining its own end after making one complete rotation. A Mobius strip. The mathematical concept wouldn't be formally described until 1858, yet here it was, carved around 3200 BCE. I spent an hour tracing that line with my finger, trying to understand the mind that conceived it. The groove was consistent in depth, about 5 millimeters, carved with confidence. No hesitation marks, no corrections. Whoever carved this knew exactly what they were creating. They understood that if you take a strip and give it a half twist before joining the ends, you create a surface with only one side, a shape that defies intuition. Dr. Hayes from Cambridge arrived 2 days later. I'd sent her photographs, but she needed to see it in person. She brought tracing paper and spent an afternoon carefully documenting the continuous path. When she finished, she sat back against the chamber wall, silent. Finally, she spoke. This isn't just a Mobius strip, it's a perfect Mobius strip. The twist occurs at exactly the right point. The line rejoins itself seamlessly. Whoever carved this understood topological properties. Topology, the study of properties that remain unchanged when shapes are stretched or deformed. It's one of mathematics' most abstract branches. The idea that a coffee cup and a donut are topologically equivalent because both have one hole. The concept that surfaces can have different numbers of sides. Modern topology emerged in the 19th and 20th centuries. Yet here was topological thinking, frozen in stone for 5,000 years. We searched the other passage tombs in the Bóinne Valley, Newgrange, Knowth, looking for similar carvings. We found spirals, circles, zigzags, lozenges, but nothing else quite like the Mobius strip at Knowth. It stood alone, unique, a singular expression of mathematical insight, or perhaps the only one that survived. How many other chambers collapsed over millennia? How many carvings were lost to time and weather? But here's what haunted me as I traced that line again and again. Understanding a Mobius strip requires abstract thinking. You can't arrive at it through simple observation of nature. You have to imagine, what if I twisted this surface before joining it? You have to think beyond three-dimensional intuition, and then you have to recognize that the resulting shape has unusual properties, that an ant walking along it would traverse both sides without crossing an edge. The implications were profound. Neolithic people supposedly concerned only with survival and basic agriculture were engaging in thought experiments about the nature of space and surfaces. They were exploring mathematical concepts through physical experimentation, and at least one of them chose to record that exploration in stone, carving it into a sacred chamber where it would wait for 5,000 years for mathematicians to recognize what they were seeing. As I left Knowth that evening, the setting sun casting long shadows across the mound, One question burned in my mind. If they understood curved space and non-intuitive geometry, what other mathematical secrets had they encoded in their monuments? And could another Irish site reveal they discovered something even more foundational? A counting system that wouldn't be reinvented until the digital age? The chamber was dark except for my flashlight beam scanning across symbols I'd never seen before. Loughcrew, another Irish site, another Neolithic mystery. But these carvings were different. Instead of spirals and circles, I was looking at what appeared to be tally marks, vertical lines grouped in patterns, separated by horizontal dividers. My first thought was simple counting. Then I started documenting the patterns, and my hands went cold. The groupings followed a sequence. 1 line, 2 lines, 4 lines, 8 lines, 16 lines. Powers of 2. Binary progression. The fundamental language of modern computing, carved into stone before Stonehenge was built. I photographed every panel in that chamber, my mind racing. This couldn't be coincidence. The progression was too specific, too mathematical. Someone 5,000 years ago was thinking in base 2. Dr. Chen, a computer scientist I'd brought along specifically for her expertise in information theory, was speechless. We spent 2 days documenting every pattern in the complex, finding the binary sequence repeated across multiple chambers. Some panels showed the progression forward. Others showed it in reverse, starting with 16 and halving down to 1. And a few panels displayed both progressions side by side, like a mathematical proof demonstrating the relationship. But it went beyond simple doubling. Some stones showed branching patterns, single lines splitting into 2, those 2 splitting into 4. Visual representations of exponential growth, the kind of diagrams we use today to teach binary trees and algorithmic thinking. The precision was remarkable. Each vertical line carved to approximately the same length, the spacing between groups consistent. This wasn't casual mark-making. This was systematic notation. We found something else that made the discovery even more puzzling. Certain groupings were enclosed in carved rectangles, as if they were being highlighted or set apart. Dr. Chen noticed these enclosed groups always contained specific numbers. Powers of 2? Yes, but only certain ones. 2, 8, 32. She pulled out her laptop and started running calculations. Those numbers, when converted to modern binary notation, corresponded to specific bit patterns used in efficient data storage. Coincidence? Or had ancient mathematicians discovered the same optimization principles we use in computer science? The question that haunted me was, why? Why would Neolithic people develop base 2 thinking? Our modern world uses binary because electronic circuits have 2 states, on and off. But what practical application drove ancient people to explore powers of 2? What problem were they solving? Dr. Chen suggested it might relate to resource division. Splitting things in half repeatedly is the most efficient way to distribute or organize certain materials. But that seemed too mundane for the careful, deliberate way these progressions were carved into sacred spaces. On our final day at Loughcrew, I found a panel that connected everything. Tally marks in base 2 on the left side, traditional base 10 groupings on the right side, and between them, carved lines showing the conversion. A translation guide between numbering systems, preserved in stone for 5 millennia. Someone had understood that different bases could represent the same quantities, that numbers are abstract concepts independent of how we choose to notate them. As we packed our equipment, preparing to leave the quiet hills of County Meath, One question pulled me forward. If Irish Neolithic people had discovered binary thinking, what mathematical insights had ancient Italians carved into alpine rock? The Italian Alps held secrets I wasn't prepared for. Val Camonica, home to over 140,000 petroglyphs spanning 8,000 years. But one cluster of carvings stopped my survey cold. Perfect right triangles, dozens of them, carved into vertical rock faces, some small, some massive, and beside them carved squares whose areas precisely matched the triangle's sides. I was looking at visual proofs of the Pythagorean theorem, created approximately 2000 BCE. That's over 1,000 years before Pythagoras was born. The triangles displayed 3-4-5 ratios, 5-12-13 ratios, even the more complex 8-15-17. Whoever carved these understood the relationship between squares and triangles, between areas and lengths. They were teaching geometry through stone. My colleague, Professor Lombardi from Milan, was practically trembling as he measured the carvings with digital calipers. The largest triangle measured nearly 2 meters on its longest side. Carved beside it were 3 squares, each side length matching one side of the triangle. And inside each square, carefully counted pecked marks indicated their areas. 9 square units for the 3-unit side, 16 square units for the 4-unit side, 25 square units for the 5-unit side. And there, carved with emphasis, an equation, 9 plus 16 equals 25. This wasn't abstract mathematics existing only in someone's mind. This was mathematics made visible, concrete, testable. Anyone could count the marks in the squares. Anyone could verify that the 2 smaller areas summed to equal the largest. This was mathematical proof you could touch with your hands, a theorem demonstrated through physical carving rather than written symbols. We found 17 distinct right triangles across 3 rock panels, each one accompanied by its squared sides, each one demonstrating the same fundamental relationship. But what made this discovery profound was the variation. The carvers weren't just repeating one example, they were showing that the theorem worked for different triangles. 3, 4, 5, yes, but also 6, 8, 10, and 9, 12, 15. They understood this was a universal principle, not a special case. But the most haunting detail? Many triangles were aligned to solar angles. Professor Lombardi brought an astronomer to verify. Certain triangles, when measured against the horizon, aligned with sunrise positions at solstices and equinoxes. The ancient carvers had discovered that geometry and astronomy were connected, that the same mathematical principles governing triangles also governed celestial movements. They were seeing patterns that unified earth and sky. I spent a week documenting every triangle, every square, every carved mark. The precision was extraordinary. Right angles accurate to within 1 degree. Proportions maintained across scales from hand-sized carvings to massive panels. This required measuring tools, probably marked ropes or sticks, and the geometric knowledge to use them correctly. These weren't primitive scratchings, these were the works of mathematicians who understood their craft deeply. On my last evening in Val Camonica, I sat watching sunset light rake across the rock faces. The shadows revealed details invisible at midday. Faint connecting lines between some triangles, barely visible arcs suggesting compass work. These carvings weren't isolated exercises. They were part of a larger geometric study, a stone textbook teaching principles that would later be credited to Greek philosophers. As I descended from the Alps, one question burned in my mind. If ancient Europeans had mastered right triangle geometry 1,000 years before Pythagoras, what had ancient Americans discovered in their desert canyons? And could their rock art reveal an even more profound mathematical insight, one that modern mathematics wouldn't formalize for thousands of years? The Utah sun was merciless as I documented the panels, but I couldn't stop. Parowan Gap, sacred to the Fremont culture, covered in petroglyphs that repeated patterns at different scales, fractals. The same design appearing large, then smaller again, each iteration maintaining the same proportional relationships. Modern mathematics didn't formally describe fractals until Benoit Mandelbrot's work in the 1970s. Yet here they were, carved 1,000 years ago. Zigzag patterns that looked like lightning but followed precise geometric rules. I measured the angles, 45 degrees, consistent across all scales. The width of each zigzag line related to its length by a constant ratio. When a large zigzag contained smaller zigzags, those smaller versions maintained the exact same proportional relationships. This was self-similarity, the defining characteristic of fractals, executed in stone by people who supposedly had no formal mathematical training. Dr. Williams from the University of Utah specialized in chaos theory and fractal geometry. I'd brought her specifically to verify what I was seeing. She spent 3 days measuring, photographing, analyzing. Her conclusion was unambiguous. These are fractals, not approximations, not close enough. These are mathematically rigorous, self-similar patterns demonstrating understanding of scale invariance and iterative repetition. Spirals that nested within themselves across 4 scales. The outermost spiral, carved about 30 centimeters in diameter. Inside it, 4 smaller spirals arranged symmetrically, each about 7 centimeters across. And inside those, even tinier spirals, barely visible, each less than 2 centimeters. But here's what made it remarkable. The ratio between spiral sizes was consistent. Each level was approximately 4 times smaller than the previous. The Fremont people had discovered self-similarity, the principle underlying everything from coastlines to clouds to the structure of lungs. Natural forms that look similar whether you zoom in or zoom out. Mathematical patterns that repeat across scales. This wasn't just artistic preference for certain designs. This was recognition of a fundamental property of nature and geometry. But the most extraordinary panel showed cross-sectional patterns. Imagine cutting through a fractal at different depths. What would you see? The Fremont carvers had answered that question. They'd created panels showing the same pattern at different cross-sections, each view revealing similar structure. This demonstrated 3-dimensional thinking about fractal geometry. They weren't just copying a 2-dimensional pattern, they understood how these patterns existed in space. I found teaching sequences, panels showing the progression from simple to complex, a single zigzag, then that zigzag with smaller zigzags added to each segment, then those segments subdivided further. It was like watching a geometric tutorial carved in stone, showing how iterative addition of detail at smaller scales creates fractal complexity. Someone was teaching this concept, passing down knowledge of self-similar patterns to future generations. On my final evening at Parowan Gap, the setting sun created shadows that revealed something I'd missed. Faint scratches around some fractals, preliminary marks showing the planning process. The carvers had sketched guidelines first, mapping out where each iteration would go before committing to deep pecking. This wasn't spontaneous creation. This was careful mathematical planning, working out the geometry before executing it permanently in stone. As I drove away from that sacred canyon, one question dominated my thoughts. If North American indigenous people had discovered fractals 1,000 years ago, what had ancient Saharan people learned while tracking the slowest movement in the heavens? The desert had swallowed most of the sight, but enough remained to change everything I thought I knew. Deep in the Algerian Sahara, rock art dating to 6000 BCE showed something extraordinary. Circles within circles, marked with radiating lines pointing to different positions. My astronomer colleague, Dr. Hassan, recognized it immediately. This was tracking axial precession, the slow wobble of Earth's axis that takes 26,000 years to complete. The ancient artists had marked multiple positions of the celestial pole, suggesting they'd observed and recorded the shift over generations. I stood in the scorching heat, staring at concentric circles with radiating marks at different angles, each mark labeled with symbols, possibly representing time periods or generations. This wasn't a snapshot of the sky at one moment. This was a time-lapse carved in stone, documenting stellar movements across centuries. Dr. Hassan brought his equipment, astronomical software that could model the sky as it appeared thousands of years ago. We photographed the rock art, measured the angles between the radiating marks, input the data. The software processed for several minutes. When the results appeared, Dr. Hassan went silent. The marks corresponded to actual positions of the celestial North Pole across a span of approximately 1,200 years. Think about what that means. Axial precession moves the celestial pole by only 1 degree every 72 years. It's imperceptible within a human lifetime. To detect it requires multi-generational observation and record keeping. Someone had to start recording stellar positions. Their children had to continue. Their grandchildren had to maintain the project. Generation after generation, measuring, comparing, noting the gradual shift, and someone had to preserve those records, compile them, and carve the final synthesis into stone. But here's what made this discovery profound. Understanding precession requires recognizing patterns that play out over timescales longer than any human lifetime. You can't directly observe it, you can only infer it by comparing records across centuries. This demanded institutional knowledge, a system for preserving and transmitting information across generations. These weren't isolated observers. This was organized astronomy, possibly the world's oldest scientific institution. We found secondary panels nearby, star positions marked with dates, possibly seasonal markers or reference points. The precession map wasn't isolated. It was part of a larger astronomical record-keeping system. The Saharan people had created an observatory without walls, using the rock faces as permanent data storage. Each carving was a data point in a multi-generational research project studying the fundamental mechanics of Earth's movement. I spent 2 weeks at that site documenting every mark, every symbol, every angular relationship. The precision was extraordinary. Angles measured to within half a degree, symbols showing careful distinction between different time periods. This required not just observation, but mathematics, the ability to calculate angles, to project future positions, to understand that celestial mechanics follow predictable patterns. On my final night in the Sahara, I sat beneath stars that had shifted imperceptibly since those ancient astronomers carved their observations. They'd looked at the same sky, noticed what shouldn't be noticeable, and committed themselves to tracking it across lifetimes. Their dedication had preserved knowledge that would eventually help humanity understand we live on a spinning, wobbling planet orbiting through space. As I prepared to leave the desert, one question pulled me toward France. If Saharan people had tracked precession 6,000 years ago, what mathematical principles had Neolithic Europeans encoded into massive stone arrangements that stretched across the Bóinne landscape? 3,000 standing stones march across the Bóinne landscape, and I'd walked among them for days before I understood. The stone rows weren't random. Photographed from above, they formed spirals, and those spirals contained the golden ratio. I measured the distances between stones, the angles of the rows, the proportions of the curves. Phi appeared everywhere, 1.618, the most aesthetically pleasing ratio in mathematics, the pattern of seashells and sunflowers and galaxies. The megaliths of Carnac, erected around 4500 BCE, were arranged according to principles that wouldn't be formally described until Euclid wrote about the golden section in 300 BCE. But the builders of Carnac didn't need formal descriptions. They could see the harmony. They understood that certain proportions created balance and beauty, and they moved stones weighing tons to manifest that understanding across kilometers of French countryside. I hired a drone pilot to capture aerial footage. From the ground, Carnac seemed like parallel rows of stones marching toward the horizon. From above, the pattern revealed itself. The rows curved gently, forming logarithmic spirals similar to what I'd seen in Nazca. But these spirals were built with massive stones, some standing 4 meters tall, arranged so their collective positioning created the mathematical curve. Dr. Rousseau from the University of Rennes joined me with ground-penetrating radar. We needed to know if removed or fallen stones had disrupted the pattern. The radar revealed stone holes, places where megaliths once stood. When we plotted those positions alongside the existing stones, the spiral became even more perfect. Carnac, in its original complete state, was a massive golden ratio spiral, built from thousands of tons of stone. But here's what made this extraordinary. Creating a logarithmic spiral with discrete points, individual stones, requires calculating exactly where each stone must stand. The spiral curve is continuous, but you're approximating it with separate objects. Place a stone slightly wrong, and the spiral distorts. Yet the Carnac stones, when properly positioned, created curves accurate enough that modern mathematical analysis confirmed the golden ratio in their expansion. I measured specific triangles formed by stone positions, selected 3 stones, measured the distances between them, calculated the ratios. Time and again, phi appeared. The ratio between the longest and middle sides approached 1.618. This wasn't accidental. The builders were using the golden ratio as a design principle, embedding it into the spatial relationships between stones. We found smaller stone circles near the main rows. These circles also incorporated golden ratio proportions. The diameter related to the circumference in ways that produced phi when you calculated specific geometric relationships. Someone understood that circles and spirals could both express the same fundamental mathematical constant. On my final evening at Carnac, I climbed a nearby hill to watch sunset illuminate the stones. The low light created long shadows, and those shadows revealed alignments I hadn't noticed. Certain stones aligned with solstice sunset positions. The golden ratio spirals weren't just mathematical, they were also astronomical, integrating earthly geometry with celestial mechanics. As I left Brittany, one question consumed me. If Neolithic Europeans had built golden ratio spirals from megalithic stones, what had ancient Americans discovered when they placed stones at high altitude to track both sun and stars? I climbed for 2 hours to reach the site, my lungs burning in the thin air of New Mexico. The Anasazi had chosen Fajada Butte for a reason. Behind 3 stone slabs, I found the famous spiral, a petroglyph that serves as a solar and lunar calendar. On the summer solstice, a dagger of light pierces the spiral's exact center. On the equinoxes, 2 daggers frame it perfectly. But that was just the beginning. I documented how the shadows moved across the spiral throughout the day and across seasons, creating a complex timekeeping system accurate to within days. This was an analog computer built around 1000 CE, calculating solar and lunar cycles simultaneously. The Anasazi had placed those 3 slabs with millimeter precision, knowing that centuries later, light would still mark time exactly as they intended. The spiral itself consisted of 9.5 turns, carved into the cliff face with careful pecking. But the genius wasn't the spiral. It was the 3 stone slabs leaning against the cliff at precise angles. On the summer solstice at midday, sunlight passing between 2 slabs created a vertical dagger shape that fell exactly through the spiral center. On winter solstice, 2 daggers bracketed the spiral symmetrically. The stones weren't randomly placed, they were optical instruments. Dr. Malville from the University of Colorado had studied this site for years. He explained how the lunar cycle also appeared in the shadow patterns. Every 18.6 years, the moon reaches its maximum declination, its highest and lowest points in the sky. The Anasazi had discovered this cycle and marked it. During lunar maximum, additional shadow patterns appeared on the spiral, marking this rare celestial event. But erosion and tourism have shifted the stones slightly. The light daggers no longer align perfectly. We're watching an ancient computer slowly fall out of calibration, and we can't fix it without knowing exactly how they set it up. I spent days photographing the current shadow patterns, comparing them to records from the 1970s when the site was first documented scientifically. The degradation was visible. Shadows that once hit specific points now missed by centimeters. Think about the planning required. The Anasazi had to understand solar geometry, how shadows change with seasons. They had to calculate where to place stones so shadows would fall in specific patterns on specific days. And they had to account for this location's latitude, its elevation, the cliff's orientation. This was site-specific engineering, mathematics applied to create a functional astronomical instrument. I found smaller spirals nearby, also positioned behind rock formations that created shadow patterns. These seemed to be experiments or teaching tools, showing different stages of understanding before the final sophisticated design. Someone had worked through multiple iterations, testing ideas, refining the geometry. On the summer solstice, I returned before dawn. As the sun rose, I watched light slowly angle between the stone slabs, and there, at precisely solar noon, the dagger appeared, piercing the spiral's center just as it had for 1,000 years. Despite the degradation, the core function remained. The ancient computer still calculated the year's longest day. As I descended Fajada Butte, exhausted but exhilarated, One question drove me forward. If the Anasazi had built solar and lunar computers from stone and shadow, what mathematical sophistication had ancient Azerbaijani people achieved when they carved circles within circles into Caspian rocks? The Caspian winds howled across the Azerbaijani rocks as I studied circles within circles within circles. Gobustan's petroglyphs date back over 15,000 years, making them among Earth's oldest. But these particular panels showed something more recent: mandalas of stunning geometric complexity created around 3000 BCE. Each circle divided into 8 sections, each section containing patterns that mirrored the others with rotational symmetry. I counted the elements, patterns repeating in multiples of 4 and 8, demonstrating understanding of angles and degrees. At the center of the largest mandala, a point from which all lines radiated with equal spacing. This was wheel geometry, the mathematics of perfect rotation, conceived before wheels were commonly used in this region. Someone had understood abstract circular mathematics before they'd applied it to transportation. The precision of the curves, carved into hard stone with copper tools, suggested they had methods of measurement and marking we've lost. I traced one circle with my finger. The groove depth was consistent throughout its entire circumference. No wobbling, no flat spots. Just a perfect circular arc maintained across nearly 2 meters of diameter. Creating this required a fixed center point and something to maintain constant radius, probably a rope or marked stick rotating around that center. Dr. Ahmedov from Baku University brought geometric analysis tools. We photographed each mandala, imported the images into software that could measure angles and proportions. The 8 sections weren't approximate. They were exactly 45 degrees each, accurate to within half a degree. The circles were concentric, sharing the same center point, each one proportionally spaced from the next. But the mathematics went deeper. Some mandalas showed nested patterns where each ring contained double the elements of the previous ring. 4 elements in the innermost ring, 8 in the next, 16 in the third. Binary progression again, but expressed through circular geometry rather than linear marks. Someone had discovered that doubling patterns could organize circular space as effectively as linear space. I found teaching sequences, simple mandalas with just 2 rings and 4 sections, more complex versions with 4 rings and 8 sections, the most elaborate panels with 6 rings and 16 sections. This suggested progressive learning, starting with basic concepts and building toward complexity. Someone was teaching geometric principles through increasingly sophisticated examples. The rotational symmetry was perfect. I could photograph a mandala, rotate the image by 45 degrees, and it would match itself exactly. This 8-fold symmetry appears in Islamic art, in Buddhist mandalas, in architectural designs worldwide. But here it was, carved 3,000 years before those traditions formalized it, created by people working with stone tools and geometric insight. On my final day at Gobustan, the afternoon light revealed something I'd missed. Faint connecting lines between some mandalas, suggesting they weren't isolated exercises but parts of a larger geometric study. The lines connected centers, creating triangular relationships between circles. Someone was exploring how circular geometry could generate other shapes, how circles could define triangles, and how those triangles could organize space. As I prepared to leave the windswept rocks overlooking the Caspian Sea, one final question pulled me westward. If ancient Azerbaijanis had achieved this level of geometric sophistication 3,000 years ago, what had Native Americans discovered when they arranged stones in the high mountains to track the movements of both sun and stars with mathematical precision? The medicine wheel sat at nearly 10,000 feet, built from stones arranged in a pattern that seemed simple until you understood what you were looking at. 28 spokes radiating from a central cairn, the exact number of days in a lunar month. But the spokes weren't evenly spaced. 6 were marked with additional stone cairns, and those 6 aligned perfectly with sunrise points on the summer solstice and the rising positions of Aldebaran, Rigel, and Sirius. The Native American builders, working around 1200 CE, had created a device that tracked both solar and stellar cycles simultaneously. But here's what made me question everything. The wheel's design anticipates the horizon as seen from this specific altitude. It wouldn't work anywhere else. They'd done the geometry, factoring in Earth's curvature and atmospheric refraction, to create a site-specific astronomical instrument. I spent a week at the Bighorn Medicine Wheel, camping nearby despite the thin air and bitter winds. Every morning before dawn, I positioned myself at the central cairn, watching stars rise over the eastern horizon. On the summer solstice, I documented the sunrise alignment. The sun appeared exactly where the marker cairn indicated, rising between 2 distant peaks in a moment of perfect geometric prediction. Dr. Eddy, an astronomer who'd studied medicine wheels for decades, explained the mathematics behind choosing this exact location. At this elevation, atmospheric refraction bends light in specific ways. The builders had compensated for this effect, placing marker cairns not where simple geometry would suggest, but where actual observation confirmed stars and sun would appear. This required empirical testing, comparing theoretical predictions with observed reality. The 28 spokes represented more than just lunar days. They divided the circle into segments of approximately 12.86 degrees each. Not a round number, but the actual angular spacing needed to mark lunar progression accurately. Someone had calculated this, understanding that circles contain 360 degrees and dividing by 28 to determine spoke placement. I found alignments to stellar risings that only occur once every several years. Aldebaran, the brightest star in Taurus, rises at specific points on the horizon that shift annually due to precession. The medicine wheel's marker anticipated where Aldebaran would rise not just in one year, but across multiple years, suggesting the builders understood stellar mechanics operated on longer timescales than solar or lunar cycles. The mathematics behind choosing this specific elevation, at this exact latitude, required sophisticated understanding of spherical geometry. Earth isn't flat. Horizons change with altitude. Stars appear at different angles depending on your position. The builders had factored all of this into their design, creating an instrument so precisely calibrated that 800 years later, it still calculated celestial events with remarkable accuracy. As I descended from that high mountain site, the medicine wheel shrinking behind me, I carried with me not just data and photographs, but profound questions. 15 sites across 5 continents. 15 examples of mathematical sophistication that predated formal mathematical theory by centuries or millennia. What did it mean? What had I truly discovered in these stones and spirals, these carefully carved proofs left waiting in silence for someone to read them? I sit now in my study, surrounded by photographs and measurements, field notes and calculations spread across every surface. The dust of 5 continents still clings to my boots, and I keep returning to the same question. What did they know? Not who were they or when did they live. Those questions have answers, dates, and cultures cataloged by archaeology. But what did they know? What mathematical insights lived in minds 5,000 years ago that we've only recently formalized? And more troubling, what knowledge have we lost entirely, encoded in stones we've stopped reading? The evidence is undeniable. The golden ratio at Newgrange, carved before the pyramids. Binary progression at Loughcrew, predating computers by 5 millennia. Fractal geometry at Parowan Gap, anticipating Mandelbrot by 1,000 years. These weren't accidents. These weren't lucky guesses. These were people who understood mathematics deeply, abstractly, and chose to preserve that understanding in the most permanent medium available. But preservation for whom? For us? Did they know their civilizations would fade, their languages disappear, their very names forgotten? Did they carve these proofs in stone because they understood that rock outlasts everything else, that mathematical truth needs no translation? I think about the Mobius strip at Douth, hidden in shadow where almost no one would see it. I think about the binary code at Loughcrew, repeated across multiple chambers as if urgently insisting someone understand. I think about the medicine wheel at 10,000 feet, built where the thin air makes every stone placement an act of endurance. These weren't casual creations. These were deliberate messages, encoded for a future they couldn't imagine but somehow anticipated. History doesn't whisper, it waits. In stone and spiral, in shadow and alignment, in proportions too precise to dismiss. The mathematics is still there, patient, eternal, ready to teach anyone willing to trace the grooves, measure the angles, and ask the simple, devastating question, how? 15 sites, 15 pieces of a puzzle still incomplete. The expedition continues. There are more stones to study, more patterns to decode, more impossible mathematics waiting in places we've dismissed as primitive. The ancients knew something, and I've learned one truth on this journey. We've only scratched the surface of forgotten worlds.